Hey folks, it's chemistry time. You're here with Miss Gray, and I'm joined by two of Mr. Henderson's fantastic students, Miss Rachel Harlow, say hello, and the lovely Anna Darrow. Yeah, Darrow, sorry. So let's get started with limiting reagents because this stuff can be a little tricky. We're going to take it one step at a time, and if you take one step at a time and every step we take is easy, we could go a long ways.
Yep.
All right, so let's take small steps that are easy steps. This is podcast 8.3, and we're going to talk about limiting reagents and percent yield. We've talked a lot about recipes in Unit 8, and so I put an example of a cake recipe because who doesn't love cake, right?
Right.
Exactly. I don't know why it's a wedding cake, though. Maybe it's just a Valentine's cake. I don't know. It's a happy cake, though. Here's our cake recipe. And in my kitchen, I don't always have exactly the amount of stuff I need. I almost always have more flour than what I need for a cake, right? Like, that's just in the kitchen. And eggs tend to run out quickly at our house because we like to eat omelets. But sugar I've got, baking powder, I always have that kind of normal stuff. They're called staples. So let's see how many cakes can be baked using the amount of stuff I've got in my kitchen. All right, so if I just look at what the flour will make, I need 2 cups, but we have 14 cups of flour. So how many cakes would that make?
7.
7 cakes. That part was easy. All right, let's try another one. We need 2 eggs for our recipe. We only have 4.
Oh, 2.
Yeah, we can make 2 cakes, right. Okay, sugar. Let's see. I need 1 cup, but I have 9 cups of sugar. How many cakes will that make? 9 cakes, right on. I better have a lot of friends over. Okay, baking powder. I only need 1.5 tablespoons, and my little container has 15 tablespoons. So that's 10 cakes. All right, finally with water, I need 1 cup, and I have 10 cups. 10 cakes, right?
Yeah.
Okay, I think the oil is our last ingredient. We need 1/3 cup. Oh, now we have fractions. 3 1/3 cups of oil. That's going to make 10 cakes. Fractions, no big deal. So then how many cakes can we actually bake using what's in my kitchen?
2.
Why only 2?
Because if you go back, it's the limiting factor.
Right, exactly. I'm going to run out of eggs before anything else. And so the most that I can make is 2 cakes. We'll have leftover flour, right? And so this is called the limiting factor, like Rachel said, or sometimes we call it the limiting reactant, and some people call it the limiting reagent. It doesn't matter what words you use, it's the one that runs out first, and we can't make any more when that one's gone. So here's an actual chemical equation. And a chemical equation is just like a recipe. This is how we can get water and nitrogen monoxide when we start with ammonia and oxygen. That's our recipe. So we have 3 examples here to look at. How many moles of nitrogen monoxide are produced if we have, in the first example, 4 moles of ammonia burned in 5 moles of oxygen. So we'll look to our recipe. Where's the ammonia? Let's see, here's our ammonia, 4 moles, and here's the oxygen, 5 moles. And so this one seems like it's going to work out just right. So we're looking for moles of NO. Here's that one. So what's the number in front of NO?
4.
4. So that one works out exactly to 4 moles of NO. But in the next example, I still have 4 moles of ammonia, but this time I have 20 moles of oxygen. Now how much of the nitrogen monoxide can we make? Can we make any more of it than we did before?
No.
You're right. We can make 4 moles of nitrogen monoxide, but we're going to have leftover oxygen. Oh, I didn't ask the question. Whoops. This time, we started with 8 moles of ammonia, and we have 20 moles of oxygen. And since we have twice as much ammonia, we can make twice as much nitrogen monoxide, right? The oxygen is not going to run out before the ammonia runs out. So we still have leftover oxygen, because let's see, if I had 8 moles of this, that means I used 10 moles of oxygen. See, I only used half of what I had there. So that one still has leftover oxygen. In this case, in all of these examples, the ammonia is the one limiting the production of nitrogen monoxide. So if there was more ammonia, we would have produced more nitrogen monoxide, right?
Yeah.
Okay, well, when we're trying to figure out how much stuff we can make, we always look at the limiting reagent. The one that we have extra of is not the one that determines how much we can make, right? Like if we're making tricycles and you only have 2 tires, you're not going to get a whole tricycle out of that. Most of the time. Unless you have a goofy tricycle. All right, so then here's our recipe. Again, same recipe. We'll just stick with it. This time, I have 4 moles of ammonia, which we know that's a good number. This time, though, we have 2.5 moles of oxygen, and I needed 5 moles of oxygen. 2.5 is 1/2 of 5. So how much NO can we make in this case?
4.
Yep. Half of 4, so 2 moles of NO. And we'll have leftover ammonia this time because I didn't use up all of it, I only used half of it. Does that make sense?
Yeah.
Okay. So much for those recipes. Let's do something hard. You ready for something hard?
Yeah.
Bring it on, right? Okay, fine. How many grams of nitrogen monoxide are produced if 4 moles of ammonia are burned and 20 moles of O2? Well, we already know how many moles that's going to be. We just answered that, right? 4 moles of ammonia. And so we're going to start a T table with 4 moles of ammonia because that runs out first. But my question is asking how many grams of NO. I'm going to circle that. I always circle my target because targets are round, so I circle them. It helps. All right, and then this is my starting amount that I put on my starting line of my T table. Now it's ready to run the race. So in my first step, I want to change moles of ammonia into moles of nitrogen monoxide. The only way that I can do that is by using a balanced equation. So let's look at the number in front of ammonia. It's 4, so that goes down here. The number in front of NO is 4. Well, this is easy math so far, because 4 over 4 cancels. I can do this math in my head.
Yeah.
Good thing you brought a calculator, Anna. Okay, what's next? Let's see. Moles of ammonia cancels, but my target is grams of NO. So I now have to change moles of NO into grams of NO. So in 1 mole, let's decide how many grams there are. We'll need a periodic table. You got one handy?
Yeah.
Okay, tell us how many grams are there for nitrogen?
14.
Okay. And for oxygen?
16.
Okay, 0.00, yeah?
Yes.
Okay, so that's easy to add, 30 grams per mole. I like it when math is easy. Okay, so moles of NO is across from each other. Remember, crisscross cancels. So moles of NO is gone. The numbers didn't cancel, but the units did. So now I'm going to take the top times the top times the top. Should we reduce this one first? We'll call this 1 and 1.
Yeah.
Yeah, I want to make easy math, right? That's the kind of math I like. So 4 times 3 is 12. That means 4 times 30 is
120.
120. And then, of course, I have this 1 hanging off the end. Then we have to divide by what's on the bottom. And since we did our reducing before, what's on the bottom is just 1. So we don't need to show that step probably. So I get 120 grams of nitrogen monoxide. I'm limited in my answer to only one significant figure. So look at what's behind the 1. Should we round that up or leave it just as a 100?
Is a 100.
Right. If it's not bigger than 5, we can't round up. And then you know what we do with our answer? Put a box around your answer. You know why? Because that's the way I like it. That's what we do. All right, let's do another example, because that one didn't seem too bad.
No, that
Right?
was hard.
Okay. This time, though, we're starting with 20 grams of ammonia, and 30 grams of oxygen. So they don't tell me how many moles I have. Guess what our first step is?
Figure out how many moles.
Figure out how many moles we have. Yeah, generally speaking, this is my advice to you in chemistry. If you're not sure how to start a problem, when in doubt, go to moles. And then you'll be halfway there. Once you know how many moles you're dealing with, you can answer almost any question from now on. Oh, my writing is in the way. My sage advice erased. So the first step is to calculate the number of moles, and we have to do this for each reactant, for the for NH3 and for oxygen. So let's do that math. I'm sure glad you have a periodic table right there. Let's figure out how many grams are in 1 mole of ammonia. So we need the mass of nitrogen,
which is 14.01.
okay, and then we need the mass of hydrogen,
which is 1.01.
okay, and there's 3 hydrogens, so we're going to multiply that. So we'll call that 3.03.
Yep.
All right, 17.04 grams of ammonia in every mole. That is mole of ammonia. And so 20 divided by 17.04. Now I'm going to let you run the show with your calculator. Okay, 20 times 1, we don't need to do that step. And then divide by 17.04.
So we get 1.13 or 1.17.
Okay, and there's more calculator vomit after that, right?
Yeah.
Yeah, we don't need all of that. But we definitely will keep all the digits in the calculator until we're done, because if you round early on, you'll perpetuate the rounding error throughout every step in your calculations, and it gets worse and worse and worse. So we'll keep that with all its digits in your calculator. But now let's do the next one, 30 grams of oxygen. Okay, so if you'll kindly look up the mass of oxygen.
16.
16, and there's 2 atoms of oxygen, so we'll double that. Some people didn't even have to look anymore because oxygen comes up so much. I bet that's when you memorized that one, and hydrogen too, probably.
Yeah.
Okay, so we got weird numbers again. Can you in your calculator do 30 divided by 32?
0.9375.
Okay, and there's probably more digits after that, right?
Not that it's shown.
Oh, okay. Well then, we'll keep all the digits. We just don't have to write them on the paper, but we keep them in the calculator. So now we know how many moles, but I still can't tell. Based on these ratios, I can't really tell which one runs out first yet. These aren't pretty numbers to deal with. So we're going to use a comparison chart in our next step. Okay, let's look and see how much ammonia do we have from our calculations. That was 1.176, we'll say, moles of ammonia, and for oxygen we had 0.937-ish moles. And now we got to figure out what we would need. So if I'm going to use up all of the ammonia, then how much oxygen would it take? So let's start with our moles of ammonia. And we're going to go to moles of oxygen so that we can see how much it would take. In our balanced equation, we know 4 moles of ammonia goes with 5 moles of oxygen. Remember that recipe?
Yeah.
Okay. So now, with your calculator, you still have that number from before?
Yeah.
All right, use all the digits. Type them all in, or yeah. You didn't store it, but it's in your screen. So just retype all those digits. I know, I always forget to store them, and then I'm like, ah, dang. Retype.
Okay.
Okay, now multiply that number by 5 and hit enter, and then divide by 4. 1.467, and then some more stuff. And that's moles of oxygen here because NH3 canceled out. So what I would need for oxygen to use up all of my ammonia is 1.467 moles of O2. what I have is less than that. So if I wanted to use up all of my ammonia, I wouldn't be able to. I'm going to run out of oxygen before I used it all up. But let's check and see, what if we started with oxygen? Would we have enough ammonia? So 0.937 moles of oxygen. And now we're going to change this into moles of ammonia to see if I can use it all up. So let's see. This time we're going to put 5 moles of oxygen on the bottom because crisscross cancels, right? So I got to put my ammonia and my oxygen across from one another. This is why it's important that you don't get lazy with writing your units into your T-tables. I know it's a pain, but you won't be able to tell which way to put it in there if you don't have all of the things listed, right? Not just moles, but moles of oxygen. Okay, this time we're going to take that other number, the 0.9375 moles of O2, multiply by 4, and then hit enter, and then divide by 5.
0.75.
0.75 moles of ammonia. Now let's compare that to what we have. 0.75 moles compared to 1.1. Oh yeah, we have plenty, right?
Yeah.
Because we only need 0.75 and we have more than that. So in our comparison chart we can see oxygen is the limiting reagent because we just don't have as much as we need. So what that means is that in our next step, oxygen is the thing that we're going to start our T-table with to figure out the answer to our question. And after all these steps, I hardly even remember what the question was. So we're going to perform the stoichiometry using the limiting reagent as the given quantity, as the starting place in our T-table. Now remember, I just said I didn't remember what the question was. That's why I put it here again, because I didn't remember. So we're starting with oxygen, right? This was our limiting reagent. Okay, so 30 grams of oxygen goes here. And our first step is to go to moles. Oh, always go into moles. So 32 grams was in 1 mole of oxygen. And now we're going to change oxygen to NO. So we go back to our balanced equation, and I had 5 moles of oxygen for every 4 moles of nitrogen monoxide. And I'm not quite to my target, but we're getting there. At least I've got NO now. Now we're going to change moles to grams. So 1 mole of nitrogen monoxide weighs 30.01 grams, right? We did that one before. Okay, calculator time. Let's see, can we reduce anything? Let's reduce right here. 5 goes into 30 6 times. Will that work?
Yep.
And then 4 goes into 32 8 times. Okay, I think that's all that we can reduce. Okay, so we'll do 30 times 1 times 1 times 6. Multiplying across the top. 180. Oh, I could have done that in my head. I wasn't thinking straight. Okay, so we have 80 grams of NO, and on the bottom, we have 8 times 1 times 1. So we'll just call that 8, shall we?
Yeah.
All right, now you can use your calculator, though. 180 divided by 8.
22.5.
22.5 grams of nitrogen monoxide. And that number has only one sig fig. 20. All right, so I have to look after my 2. We'll have to call this 20 grams of nitrogen monoxide. And we put a box around our answer. Do you remember why?
Because that's the way you like
Exactly. I'm so glad you're catching on. Great, so that's how we do a limiting reagent problem. We basically have to figure out which of our terms is the limiting reagent and then use that in our T-table. Okay, that's a lot of work, right?
Yes.
Yeah, that was 3 steps and then solving the problem. There's got to be an easier way. And guess what? There is an easier way. Okay, so here's the easy way. The shortcut. This is like the happiest part of chemistry. There's a shortcut? Yes, there is. All right, so we're going to do 2 separate calculations using both given quantities. And for limiting reagent problems, look, the smallest one is the correct answer. Because that one, obviously, it ran out first, right? So here's the same question as before. We have 20 grams of ammonia and 30 grams of oxygen. It seems like 30 grams is bigger than 20 grams, right?
Yeah.
Wouldn't we run out of 20 grams first? Well, here's how we do it. Let's do a T-table starting with ammonia. And we've already added up these molar masses, so this will go quickly. We have 17.04 grams of ammonia in 1 mole of ammonia. Now we're going to change moles of ammonia to moles of nitrogen monoxide. That's our target. So let's see, that was 4 to 4, right? 4 moles of ammonia. Oh yeah, it's right here. Ah, there, 4 to 4. I don't have to guess. Use the equation. And now we'll change moles to grams. 1 mole of NO was 30.01 grams of NO. And then we'll do all that math and magically turn up with 35.3 grams of NO. I'm not going to put a box around this one yet because I don't know if that's my answer. We have to do the other T-table and see what we get. This is the same T-table that we just did, right? So 32 grams of oxygen for every 1 mole of oxygen. And then we had 5 to 4 this time, 5 oxygens to 4 nitrogen monoxides. Whoops, that should be moles right there. Do you remember where these numbers came from? They're up here in our recipe. Okay. 5 oxygens and 4 NOs. That's an important question to ask. Okay. Wait, where did those come from? They come from our recipe, the balanced equation. All right, now let's change moles of NO into grams of NO. 30.01 grams still in every mole. And that comes out with 22.5. So now let's compare our 2 answers. Which one gets a box around it?
The smallest.
The smallest. Hey, that's what we got before. How about that? And so does this seem easier than all the steps we did before with a comparison chart?
Yes.
I think so too. I like the shortcut method, but sometimes you have to understand the long cut before you can take a shortcut. So whichever way you prefer, I don't mind. Okay, so this time we're going to do an example with the shortcut. We have 25 grams of aluminum added to 90 grams of hydrochloric acid. So we want to see what mass of H2 will be produced. Seems like aluminum would run out first, yeah? 25 grams is smaller than 90 grams.
Yeah.
But it's not about grams, it's about moles. So we have to do a comparison here. So 25 grams of aluminum, I need that periodic table. How many grams are in 1 mole? Remember our first step? When in doubt, go to moles.
26.98.
26.98 grams of aluminum for 1 mole of aluminum. And then we'll use our recipe. We're going to H2. So every 2 moles of aluminum makes how much hydrogen?
2 grams? Or 1 gram?
3.
3.
See, two of these makes 3 of these.
Okay.
Okay. And then we're trying to get to mass, so we have to change moles to grams. That's okay. Hydrogen's easy, right? What's the number of grams for hydrogen?
1.
Oh, okay. And H2 is going to be 2. All right, so time for a calculator. I don't see any easy reducing anywhere, so we're just going to do it all. Do 25 times 3 times 2.02.
151.5.
Okay, that's going to be on top. And on the bottom, I have 26.98 times 2 times 1.
53.96.
Okay, now you know what to do. Top divided by the bottom.
2.8076. Do you want to keep going?
Nah, we're just going to have to round it in the end anyway. Okay, I'm not going to put a box around this answer yet because I'm not sure that it's the smallest. Let's start the next time with 90 grams of HCl. So 90 grams of hydrochloric acid. How much hydrogen can we make from 90 grams of hydrochloric acid? So let's see, periodic table time. What's the mass of chlorine, please?
35.45.
Okay, and hydrogen is 1.01, so we're up to 36.46, yeah?
Yes.
Okay, and then our balanced equation has a ratio here, 6 HCl's. So I'm going to put it diagonal, so crisscross will cancel, moles of HCl. And then above that, I'm changing it to H2. Hey, I see something I can cancel easily. Look, 1 and 2, all right. And grams, 2.02 grams of hydrogen is 1 mole of hydrogen. Okay, so you ready for calculator time?
Yes.
Let's do 90 times 2.02 for the top.
181.8.
181.8. And that's grams of hydrogen. And the bottom is 36.46 times 2 times 1.
72.92.
Okay, take the top, divide it by the bottom.
2.493.
493 grams of hydrogen. Okay, Rachel, which one gets to have a box around it?
The smallest, so it's the bottom one.
That's right, the smallest one. And I think we're limited again to only 1 sig fig. But let's just pretend like I had 2 sig figs because that's annoying me. So we'll call it 2.5 grams of hydrogen. Who knew? I thought aluminum would run out first. I was wrong. How about that? Okay, well, I think we're at a good stopping place. Yep, because now we're on to percent yield, so we'll save that for another podcast.
Okay.
Thanks for your help, girls.
Thank you.